Hi, my name's Drew Griffin, and I'm the Director of Sales for Nanosurf here in the US and Canada. I'd like to talk to you a little bit today about the comparison of surface metrology and imaging techniques. To get started, I'd actually like to ask you a question. So what is the right instrument for investigating my surface at the nanoscale? To answer that question, we're going to probably have to ask a couple of more questions. And then the point of our talk today is to go through and think about how we can answer these questions effectively so that we can choose the right system for our measurements. So question one, what kind of questions do we need to ask? What are the differences between the measurement techniques? And lastly, is there a single instrument that works best? Or might I need to make multiple measurements and multiple techniques to get after the data that I find effective? So I'd like to go over the brief agenda for our talk today. Number one, I'd like to go over some abbreviations and definitions. Number two, I'd like to talk about an overview of surface imaging versus metrology, and then make a comparison of the metrology techniques: electron microscopy, AFM, optical and stylus profilometry. I'll talk about the resolution and scale because that's really important to dictate what we measure and make sure that we get the right answers for what we want to see. We'll compare the techniques. I'll give some real world examples. And then because this is Nanosurf and we are an AFM company, I'm going to talk about where AFM in particular excels in imaging and metrology. So some brief definitions, of course, if you may already know these, but just to get us on the same page, AFM stands for atomic force microscopy. SPM is an analog to that, which is scanning probe microscopy. It may even be a more catch-all term than AFM itself. This comes in many different flavors, so we'll talk about some of them today. SEM, TEM, and EM, those are all different types of electron microscopy for the purposes of our discussion today. We'll talk about optical and stylus profilometry. Optical will use light as a probing mechanism, whereas a stylus profilometer will actually use a physical stylus. And then I'll actually explore a little bit the differences between imaging and metrology as it relates to our samples here. So I do want to go over the differences between what I would consider surface imaging and surface metrology. Again, my definitions are going to be skewed a little bit towards the purposes of this discussion, not necessarily being 100% fully accurate. But I'm going to consider surface imaging to be what we would do if we created a two-dimensional representation of a three-dimensional surface. Basically like taking a photograph. X and Y will be encoded with dimensional information, so we could actually make measurements for the size of things in X and Y. But any topography we recorded in surface imaging is going to be purely qualitative. Whereas surface metrology in this case will make a full three-dimensional representation of the surface where all three axes, X, Y, and Z, would be encoded with dimensional data. So to give you an idea of the different techniques we're going to discuss today, I would consider electron microscopy, AFM, and optical profilometry to be surface imaging techniques. I would consider AFM and the two profilometries to both be metrology techniques. And you can see that not necessarily everything is a catch-all, that electron microscopy doesn't do such a great job in metrology, and stylus profilometry doesn't necessarily do a great job in imaging. Again, we can always think of exceptions to the rule, but as a principle for this discussion, this is how we're going to define everything. So I do want to give a quick background of each of the techniques. So electron microscopy is a nanoscale imaging technique which uses the acceleration of electrons rather than visible light as an illumination source. To give you an idea, a typical electron microscope is shown here on the left, and a rough working diagram of the system is shown here on the right. If you're familiar with how optical microscopes work, you'll notice that an EM schematic is actually similar to that of a light microscope. The biggest difference is that we'll use magnets and electromagnetic coils as our condenser lenses, and as opposed to using pieces of glass to focus the light. Here's an example of measurements that we can make with an electron microscope, especially something that's maybe a little more metrology based. You can take an example of 4 different surfaces that were scanned with an electron microscope here. They're all recorded with the same XY dimensional data, but you can physically see that there are differences in topography between each of the 4 regions. For example, S40 appears to be considerably rougher with much larger features than, for example, S20 in the upper right. But we can't necessarily put a number to what these values are. So it's a great comparison technique. I can say, yeah, this looks good, this looks bad, but I couldn't necessarily make quantified numbers based on the data that I would pull from the electron microscope. Optical profilometry, it can come in many different flavors. And again, I'm going to speak relatively broadly here. I do want to note that they can come in such flavors as, like white light interferometry, or a confocal laser scanning. There's chromatic aberration. There's focal variation. By and large, I'm going to kind of just use optical profilometry as a catch-all here. We could probably host an entire webinar on just the different techniques within optical profilometry, or really any of these techniques that we're going to discuss today. You can see here, there's an example of a white light profilometer on the left. It looks a lot like an optical microscope. And here's the working diagram of one example of white light optical profilometer. In fact, an optical interferometer here on the right. And what you'll notice is that when we correct the data with our optical profilometer, we will get something that looks like an image. It will be false color contrasted and encoded with Z dimensions. So you'll notice in each of these images here on the left, we actually have a Z dimension that's now measured on our scale bar to go along with our XY measurement. We can measure a variety of textures, and we can quantify these textures. And again, we can both qualitatively look at them, and then we can quantify the differences between the two, or between each of the samples here for further measurement. A stylus profilometer, it's probably actually the easiest system here to understand. Everyone has a finger, which is basically a stylus profilometer. And similar to the way that a blind person would read Braille, a stylus profilometer will read the texture of a surface. It works just like an old-fashioned record player in a lot of ways, where the stylus is actually reading the bumps and contours of a surface. But rather than playing back the data it reads audibly like in a record player, it will just record that into a line, and then we can actually use this line to actually make topographical measurements. Take a look at some example data from a stylus profilometer, here are a couple of different line traces. If you take a look at the trace on top, this is a trench that's being measured at approximately 180 nanometers deep or so. And we can see on the bottom surface, we have a step height, which would most likely be a thin film that was deposited. We're measuring the thickness of that film in the function of this step height. Lastly, I'd like to talk a little bit about atomic force microscopy. It is very similar in operating principle to a stylus profiler. It's going to use a sharp probe to probe the surface, but rather than just draw a line, an atomic force microscope has an XYZ scan engine that's going to let us raster our probe back and forth very quickly to build a three-dimensional map. And also, rather than using just a blunt stylus, we're going to use typically an etched silicon probe with an end radius on the order of a few nanometers. And we're going to sense the surface by doing something that's called optical beam deflection. Almost every AFM in the market will take a laser. It will bounce that laser off the back side of our cantilever and put that reflection onto a 4-quadrant photodetector. And so any perturbation of that cantilever in any direction is going to be sensed by a change in the location of the spot on that 4-quadrant detector. And what an AFM really does in practice is, as we move the stylus of the AFM probe across the surface, we're going to be displacing that spot on the center of the probe. And then the feedback mechanism of the AFM is going to move the probe in X, Y, or Z to compensate for that, to try to recenter the spot in the center of our detector. And that's actually going to record the output of the data it used to recenter it as our topographic image. AFM is a very high resolution technique. So you can see here in these examples, we have an atomic lattice of mica. And so you can see that we're actually able to see the lattice structure of fixed crystal. And we can actually quantify the distance between the different atoms in the mica. And this is considerably less than 1 nanometer. Again, the range, the XY range on that image in the upper left-hand corner is 6 nanometers, and we're seeing features that are much smaller than that. And we can also look at larger items as well. So this is a repeating silicon structure. It has a height of about 50 nanometers. It actually has an XY displacement between each of those little pads of about 50 nanometers as well. So some of you, we're going to take a little bit of a turn here as we start talking about resolution and scale. And I want to ask you a little bit about the question of which landform has the longest coastline, Norway or Africa? You can see in the pictures that are here on your screen, Norway is considerably smaller than Africa. And I think intuitively we would look at this and say, if we asked our 5-year-old selves this question, we would probably all answer, well, Africa's bigger, therefore it must have a larger perimeter. But if we start exploring this in detail, how do we measure this? And what is the real answer? So I took it upon myself when building this presentation to hop on the Google Maps and start to try to put a quantifiable measurement to the perimeter of Africa. And I said to myself, well, I need to do this in a reasonable amount of time. So I'm going to use 100-mile segments to measure this. I'm going to basically draw around the coastline. I'm going to get a number. I'm going to assign the coastline length of Africa. And if I did that, it came out to be about 15,000 miles. So it's big. And I look at Norway and I'm like, there's no way that Norway is anywhere close to having a coastline that long. So I went into Google Maps, I zoomed in, I used that same 100-mile discriminator length. I measured the coastline of Norway, and lo and behold, I was right. Norway's coastline is much shorter than Africa's. Look, it's 1,500 miles, so it's almost an order of magnitude smaller. But I started noticing when I looked at this a little bit in more detail, it seems like I'm missing a lot of information about the Norwegian coastline. There's all those little inlets and fjords that you can see here, and islands, and my discriminating factor of 100 miles doesn't really let me capture that data. So I thought to myself, well, what if I just zoomed in a little bit more, and I used, instead of 100 miles, I used 20-mile increments. Does that affect the measurement that I'm going to get? Well, lo and behold, it does. And all of a sudden, I almost triple the length of the coastline I measure here to get about a 4,000-mile long coastline for Norway. Now, even at this discriminator length of 20 miles, I still feel like I'm missing a lot of data here. So I did what any good researcher would do, and I consulted my sources, and I went on Google, and lo and behold, the World Factbook told me that the coastline of Norway is actually over 34,000 miles long. And it listed the coastline of Africa at almost 19,000 miles. So that old adage that one of my elementary school teachers told me does kind of boil out to be true, that the coastline of Norway is in fact much longer than the coastline of Africa. So you might ask yourself, great, we're talking about different measurement techniques for things at the nanoscale. Why is this guy talking all about maps? Well, that's because what happens at the macro scale is a great analog for what happens at the nanoscale as well. So if we wanted to compare a typical random surface that we wanted to characterize, and let's assume a length of 10 microns just randomly, the length at which we measure that is going to greatly affect the numbers that we're going to see. So for example, if we did a high resolution scan where we basically, let's say, scanned it at infinite fidelity and we totally matched our surface, we would get a representation with our instrument that's very close to the surface that we see. If we increase the size of our discriminators to be about 1/10 of our measurement surface, we get a very different surface that the instrument is going to use as its measuring platform. And again, as the resolution decreases, our representations continues to change and change and change. So what does that kind of look like in practical terms? Well, if we take the same surface and we measure it with, let's say, for example, increasing tip radius, which is one way of applying what is appropriately a mechanical low-pass filter, you'll notice that number one, we can look at these four surfaces, and even though they're the same, they look very different. And number two, as we start to quantify them, we can actually see that the roughness value that we record actually decreases. So you can see from the upper left-hand corner to the lower right-hand corner, if we increase our tip radius by a factor of 25, we effectively have the resultant roughness value that we can see for that surface. Now, what's really important to us as the researcher is what length scale do we want to measure on, and what do we really care about? Because there may be very valid reasons that we want to zoom in and see the high fidelity measurement, but there may be also times when we're actually looking at much more global phenomena, and a lower resolution will suffice. And this brings me back to my next point, which is the instruments actually effectively they will choose these discriminating factors for us often just by the inherent nature of the measurements and their limits of themselves. So the effects of this coastline paradox actually are very relevant when we're thinking about the different measuring techniques for surfaces. So for example, each of these instrumental effects will actually lead to different results. And it's up to us as the researchers to decide which of these results are quote unquote correct or reasonable for our own needs. So I'd like to look at the kind of the specifications and the comparison of techniques kind of specifically for each of these, each of our 4 techniques that we've discussed so far. So if we look at the top line here, you'll notice that the imaging resolution for the AFM and electron microscope, both in X, Y, and even in Z, are typically considerably better than that of the two optical and stylus profilometry measurements. However, not necessarily. It may not necessarily matter because, like I said, it depends on the scale of the measurements which we want to make. The other things that actually are affected by the instruments themselves are things like the maximum field of view. So how big of a measurement can we make with each of our techniques? How fast can we make those measurements? You know, we could get ultimate fidelity, but if it takes us forever to do so, that's not necessarily practical. Some of these techniques actually give us additional information besides just the topographic or the photographic picture of what we're looking at, and that can be interesting as well. There are varying degrees of difficulty for using each of these techniques. So sometimes we just need a quick and dirty measurement. We want to do it fast, and we want to be able to train our most baseline technician to do so, and that might direct us in a particular towards a particular instrument versus the other. And then lastly, you know, some of these techniques, as we use them, they can actually damage the samples that we measure. So are we willing to, as researchers, maybe destroy or throw away or risk damaging our samples? And that might lead us towards the correct measurement technique that we care about. I do want to kind of compare these techniques graphically. So we look at those features in that table, and it's nice, but what does that actually mean kind of in real world graphical terms? Well, it gives us an idea of the measurement window of each of these tools. Now, I kind of plotted this out logarithmically, so you can see as we move through the macro scale, tick marks on each direction, we're increasing by an order of magnitude. And what you'll notice is that AFM in the lower left-hand corner is a relatively high resolution technique. We can measure very small lateral features and very small vertical features, but the upper limits of the AFM are actually kind of, they truncate off in, let's say, the tens of microns feature size approximately, both in X and Y as well as Z. If we compare that to the electron microscope, and you could probably even open these brackets on the electron microscope on the top and on the right hand side a little bit more, we can measure to a similar high resolution in the nanometer scale, certainly, but we can also measure objects that are much larger. I'm sure you've all seen the SEM images and art competitions where people will put like a grasshopper you know, or something that's actually macro scale in our eyes, or things we can actually tangibly touch, and we can still measure that with SEM with relative ease. The optical profilometers, again, also, they tend to have a very high resolution in the vertical range, so they're good at measuring things that are very flat, but their lateral resolution is considerably lower than either of the other 2 techniques we've discussed so far. And again, optical profilometers, because they are optical and they are relatively fast to acquire data, we can typically stitch images together. So within one field of view, we have a particular limit, but we can actually stitch together images to make them much larger than even what we see here in this graph. And then our stylus profilometer, lastly, again, it kind of overlaps in this very high vertical resolution, but not quite as high, or not quite as high fidelity in the lateral direction. But again, stylus profilometers, as they're typically making line traces, can measure things that end up being very long. So it's not uncommon to make a stylus trace that ends up being millimeters or potentially even centimeters long. And then not just in terms of the physical resolutions of the instrument, each of these techniques can actually operate in a variety of different measurement conditions, and that's important to consider as well. So if you've ever used any of the electron microscopy techniques, by and large, they default to operating in a vacuum. The electron guns and the electron beams operate with the highest efficiency when there's no gases in the way to perturb the electrons as they travel through their path. That means your sample also has to be put in vacuum. Our other 3 techniques operate, again, in general, in ambient conditions. Do we have the ability to potentially control the temperature? I would argue that yes, in the electron microscope, it's not uncommon to have heating and cryo stages that are available. And because it's in vacuum and you don't necessarily have to worry about damaging your components by heating it up, because you don't necessarily have that convection in the vacuum, you can actually heat to a relatively high or cool to relatively low temperatures. And again, for our ambient AFMs, we have AFMs that are available in the market easily go from sub-zero to a few hundred degrees C, depending on design. Now you can buy secondary or tertiary third-party stages that would go onto our optical and stylus profilometers, but by and large, that's not something that's done very common. Can each of these techniques image in liquid? Well, the answer is AFMs and stylus profilometers can relatively easily, and the other two can do it with pain. And again, that's talking about these third-party accessories that might make things a little bit more cumbersome. It's not routine. And again, can we operate in a controlled environment? What can we operate in liquid? Can we operate in a gas cell? Can we replace the environment around our measurements? And that's something that actually AFM excels at doing. It's very easy to put an AF in a glove box, or have a sealed cell where your AFM measurement is actually happening, is occurring inside a cell on the samples in atmosphere otherwise. And then again, the other question is, how big is the biggest sample we can measure on this? Electron microscopes are typically limited to something that's on the order of about a foot cubed, or 300 by 300 by 300 millimeters. That's the size of the vacuum chamber. Depending on the AFM design, we can be limited to a sample that's only a few millimeters or a few centimeters in diameter. Or if we're using a tip scanning AFM, I mean, you could put the AFM on an airplane wing and measure the roughness there. Optical profilometers, again, if it's a desktop system, it may be a sample that's a few centimeters in diameter, or they're certainly handheld or large format systems that can measure very large objects as well. And stylus kind of follows along in that same vein. So to kind of summarize each of the techniques, not necessarily from a specification standpoint, but from the key advantages, or why would we be driven towards each of these techniques. Electron microscopy offers excellent imaging. It's easy, and it gives a representational image that's very similar to what we'd be used to looking at either photographically or under an optical microscope. It's flexible for sample sizes and shapes. It's relatively easy to use, and there are also detectors and other add-ons available that can get you secondary and tertiary informations. Things like chemical information or crystallographic structure, structural information, whatever that might be. AFM's key advantages is that it's by and large the highest resolution XYZ system available. It operates in ambient conditions, and again, it also has many modes that are available in addition to its base topography. If we think about optical profilometry, it's really the fastest of three-dimensional topography of any of the techniques. It can take a couple of seconds to get a really high resolution, high fidelity representation of the surface. It's typically non-destructive because it's made of light. Because you're using an optical microscope, you can change the objectives of the field of view sizes, and that changes your image very quickly from millimeters to microns to nanometers in scale. And again, it collects this data, all this 3D data in a single frame by and large. And I would say for stylus profilometry, they're quick and accurate. They can scan very long distances, and by and large, they're relatively infallible. Now, we can find exceptions to that at any time as well, but it works on pretty much all samples with care. It's also, fundamentally speaking, usually the least expensive of these techniques as well. But just as anything in life, the sword cuts both ways. Our advantages can also be disadvantages as well. So electron microscopes have to work in vacuum. Electron microscopes generally struggle with charging issues. We're putting an electron beam, and if something is insulating, it will build charge up, and that can cause issues. It can struggle with light element imaging and analysis. It can be very destructive to the samples. It's not uncommon to burn things away. And again, it's really hard to get three-dimensional true surface metrology with an electron microscope. AFMs, we're really limited in our scan volume size. So this is something where we can only scan tens of microns really in X and Y, and about 10 microns in Z. Compared to the other techniques, It's typically seen as a slow scanning technique, so it's longer to get the information. And there are potential for scan artifacts, which is something we could talk about. Again, we could have a whole webinar about AFM scan artifacts historically. Optical profilometry, there are just inherent disadvantages to working with optics sometimes. Materials with different refractive indices can give incorrect measurements. Transparent samples can be troublesome. Samples with thin films can be troublesome as they can sometimes interfere with the measurement itself. And again, depending on the technique, steep slopes or sharp edges can lead to data loss. You have to be really careful when working with an optical profiler, because it's actually very easy to sometimes generate wrong data. And that's kind of the worst data of all. And then lastly, with stylus profilometer, it's comparing to the other techniques, it's relatively low resolution. Although it can do 3D imaging, it's incredibly painful to do so. It is very easy to turn a stylus profilometer into a scratch tester. You know, you put too much force or use too sharp of a probe, and it's really easy to damage soft surfaces. And again, the resolution is tip radius dependent. So in order to maybe measure that soft surface, you might end up with a tip diameter of, you know, hundreds of microns, and it gives you almost no lateral resolution whatsoever. So I'd next like to pivot and talk a little bit about some real world examples. In this example, we can actually see an AFM and an optical profiler image of the same surface. This is a CD-ROM with debris on top. And this really highlights the difference between the two techniques. The optical profiler gives you a large area scan of the topography of the material, and the AFM can then zoom in past that debris and look at things like the pits in the bits of the CD-ROM itself. Another example, we can actually use an AFM in a mode called fluid FM to electrochemically deposit metal on the surface. I show this because this is another combinational mode, where in this case we were actually able to grow these pillars of copper in solution. But in order to characterize them, we actually used an electron microscope. We knew that we were able to make an array of these copper pillars, but it would be really difficult to image these with anything other than the electron microscope because of the sharp angles and the delicate nature of the material itself. And again, the electron microscope gives us really rich, detailed images that we can go in and we can look and just as humans appreciate. I mean, look at the structure on each of these twirls that we were able to make. What we can't do here, as I mentioned before, is actually quantify the texture values of that, but there's still a lot of information here nonetheless. Example 3, this is a great example for why you would want to use a stylus profiler. This is a biosensor. That biosensor is made with different metal deposits and track deposits on a PCB board. And one of the things you might want to do, especially in manufacturing and quality control, is make sure that your trenches or your layers are the right size and depth and diameter. In this case, we were able to measure that area pointed up by the angle and verify that that trench is actually on the nanometer scale, which is intended to be, which is about 12 nanometers. And then this is an example of something you might want to do with an optical profiler. This is a scratch test that I made onto a metallic surface. But I wanted to characterize not just the scratch itself in terms of its optical view, but I wanted to go and be able to make some measurements on the depth and the amount of material that was removed. And by stitching together multiple images here with an optical profiler, I can do just that. One, I can get a nice qualitative feel for what the scratch looks like. I could have, if I was going to assign some sort of critical load or damage values, I could do that easily. But I can also measure the maximum scratch depth that was created, as well as the amount of material that was removed from the trench or piled up at the end. So now comes the commercial part of this talk. Where does AFM excel in imaging metrology, and what can we do? Where can we add value that you can't get from any of the other techniques? Well, the simplest thing is to go back to that graph I showed you earlier and notice that there's that whole area where we don't see any overlap down at the bottom left-hand corner. And in addition to that, I can go back to our comparison and contrast chart, and we can zoom in and we can find the areas where AFM had green, was able to do things that we didn't necessarily see with any of the other techniques. So for example, we could do very high resolution nanoscale measurements. We could do multi-parametric measurements, like what I like to call topography plus. So we could measure topography and then do something else. And then we could do non-destructive nanoscale metrology in ambient conditions. So you might think to yourself, what are certain types of applications that exist where AFM excels? So for example, in 2D materials, AFM gives you high resolution data, the ability to maybe do some electrical characterization at the local level. We can look at polymers and elastomers. We can dive into cell mechanobiology for some of us that are into the soft and squishy stuff. We can look at biomolecules, proteins, and DNA. We can look at thin films. There's the structure, the thickness, the mechanical properties, whatever's there. We can also look at applications of things where, like energy creation and storage, where we may want to actually run experiments where the AFM is an observer to a secondary or tertiary process. So I'd like to now kind of step through and give you some examples to kind of get your brain churning and thinking about what you basically put some data to what I just mentioned here. So this is an example of a two-dimensional material looking at an atomic step of an image that also where we've done a surface potential measurement on it as well. So you can see that we can see the triangle shape of our MOS2. We can measure that step height to be just about 600 picometers or so. And then we can actually measure the charge difference between the MOS2 and the substrate to be about half of a volt. We can look at graphene, where we've deposited graphene on copper. So on the left-hand side, we can see the topography. Once we've deposited that graphene, we actually were able to oxidize off the graphene and then do a surface potential measurement, which we call Kelvin probe force microscopy. And we can then measure, not only can see the step height, but we can see where we see differences in the resultant surface potential changes. And what's interesting here is not that we see differences between the yellow and the blue region, but in the upper right-hand corner, we see a green region as well. So that shows us that we may have had a second or third or fourth layer of graphene present, and we didn't get quite the same surface behavior when we oxidize it away. We can look at polymers. We can look at the topography of the polymer on the left, which is relatively bland of a relatively bland image. We can actually look at the phase of the image on the right, and the phase is the mechanical contrast between the SBS and the polystyrene blend. So what that tells us is that one of the polymers is significantly stiffer or more adhesive or a combination of both. And we could use that to zoom in and zoom out and look at these nanoscale properties. So you can see this is a bit of a fractal surface where we have large bubbles and smaller bubbles. And if we zoom in, this pattern tends to repeat itself all the way down to the polymeric chain level. As I mentioned, we can do mechanical biology on living cells. So one of the big attributes of AFM is that we can work in liquid and we can work in situ. In this case, we took a living cell, we had it mounted in a petri dish on an optical microscope, and we were able to do an array of force curves to measure not just the topography, but the mechanical stiffness of the cell as it varies across the cell. And then from cell to cell line, we can look at the different pathology behaviors. If we take a cell that's been, let's say, infected with coronavirus, does that mechanically change the cell? And what's really cool is that we get a nice distribution of the cell stiffness, and we can look at the different instances between the cells and the substrate. These cells generally have stiffnesses that are on the order of pascals to hundreds of pascals. And AFM is a great technique to be able to measure changes in stiffness accurately for materials that are actually very, very, very soft. I mentioned DNA. Here's an example of measuring DNA on mica. So we took DNA and deposited it on mica. It's fixed to the surface via just ionically based on the charge of the ions in solution. And we can zoom, and we can image both at kind of a lower magnification. We can actually zoom in, and we can start looking at things like, we can verify it is DNA. We can look at the minor and major grooves. And this is a relatively straightforward experiment to do. Looking at a different biomolecule, this is a surface of Bacteriorhodopsin. What we can see in the AFM is that we can see the repeating trimer structure of the Bacteriorhodopsin. We can see this at very high resolution. If you look in the lower right-hand corner of that left image, you can see those trimers, and you can see the scale bars 5 nanometers. And that's relatively easy to see. And then if we look at the FFT with our discriminating resolution borders, you can see that we're seeing resolution that is actually well below a nanometer in this image. Again, I mentioned polymers. We can do different types of polymer blends, and then we can actually look at topography, which on the left is a relatively uninteresting image, and we can start looking at mechanical contrast, in this case via force modulation. So we can look at in terms of amplitude, the amplitude signal or the phase signal, and it lets us see the difference in mechanical stiffness between the different regimes of our SPS in our methacrylate substrate. We could do just mechanical analysis. Again, these are force curve arrays of polymer samples. In this case, it is a quote unquote stiff polymer, which is about a megapascal or so, and a softer polymer, which is in the hundreds of kilopascals. And we can also quantify not just the elastic modulus, but we can actually quantify the adhesion force as well. And that's because if you look in the upper right corner, an AFM can make an array of force curves where we actually have the force curve data at each pixel. And then once we have that force curve data, we can interpret this in a variety of different ways. I'm going to go through these next couple of slides relatively quickly. It is 3 different rubber samples that are impregnated either without, with, or with a lot of different carbon filler. And here you can see we have mechanical contrast of just the rubber itself, based on the surface. The surface changes in mechanical. Basically, the domains of different mechanical differences of the surface. But as we start to put in carbon fiber filler, we start to see that the differences between the rubber itself are actually relatively low when compared with the stiffnesses of the carbon fiber filler. And if we look at a lot of carbon fiber filler, we can see that we start to get these large domains of mechanical analysis. So AFM is a great way to quantify, for example, the degree of blending of materials of 2 different mechanical stiffnesses. We can look at thin films, in this case, really thin films. These are atomic steps of strontium titanate. And we can optically very clearly see the image on the left, which gives us the step heights we can see by eye. But then, as I mentioned before, this is a topography technique. We can go back and measure those step heights. So each step's approximately 400 picometers. And we can quantify that out in the histogram analysis to give us a really good idea of those heights and the coverage there within the image. We can also look at functional properties of materials as well. So in this case, we're looking at a thin film of PZT, which is a piezoelectric material. And we actually turn the AFM into a localized piezoelectric probe via a technique called piezo force microscopy. So in this case, we'll bias the AFM probe, we'll bring it in contact with the surface, and we'll actually locally excite or switch the domains, and from not active to piezo response active. We can measure the magnitude of which they are responsive to our electrical bias, the direction in which it moves, and then we can actually quantify out D33 constants if we so choose as well. We can do other functional analysis. In this case, it's silver nanowires, and we can find out which wires are conductive versus which wires aren't conductive. Or, as I mentioned before, we can do some of these in situ analysis as well. In this case, we can do electrochemistry on a surface where we can deposit and then etch away, in this case, copper onto a gold film. So we can run in solution with the AFM probe, cyclophotometry for an electrochemistry experiment, see where we nucleate and then grow a structure, and then if we reverse the bias in the cell, we can then strip away that deposited material, and we can measure it discretely for size, for rate, for example, depending on to see how it grows. So, getting to the end, I know it's been a lot. I've got some conclusions. So at the beginning, we asked the question, what is the right instrument for investigating my surface at the nanoscale? And to answer that question, we explored we basically generated some other questions. How big is our sample to be measured? What resolution do we require? Do we need to image it, just take a picture, or do we want to characterize the surface in more detail? Can we put the sample vacuum? Can we risk damaging or destroying it? And then the answers to these questions, and maybe some other ones you can think of, will lead us towards a particular measurement technique that we've outlined here. And again, often it's not just one technique, but maybe multiple techniques as well. Excuse me. So therefore, I would postulate that a complete materials research lab should actually contain multiple methods for surface imaging metrology. These methods are all complementary to one another, and you can learn things And the more information you can gather about your sample or your system, the better results you can make for characterizing things in the future. The scale of the features that we require to measure will dictate which system is best. But again, like I said, oftentimes multiple platforms will be needed. Our stylus optical profilometry will offer fast results to surface texture and feature measurements across a very wide variety of sizes. But AFM and SEM will actually offer a much more flexible imaging platform than those other two, based on the scales and the other things you're able to do with them, mechanical or chemical analysis. And then lastly, although it may be often overlooked when compared, especially compared to electron microscopy, AFM is really a great way to get additional rich information about your materials. And it can give us information that sometimes you can't operate or access in any other way. So with that, thank you, and I'll happily take any questions.
Thanks, Drew. That's pretty good. I hope it was useful to everybody else. So if you have questions, please type them into the question and answer tab on the bottom of your screen. So before we get into question and answers, just a couple of things. The recording of this webinar will be available on our website. We'll try and get it there by middle of next week. And also, we have a few more of this webinar scheduled. We also have a few demos scheduled. So please follow us either on LinkedIn or check our website, and hopefully you'll also get emails from us. So, I think the next one that we have is next week. We have a demo of the Flex to image 2D materials. Hopefully we'll be able to get some good images like the metallic flakes that Drew just showed. So so there are a couple of questions. So yeah, one question is, can we have a recording of this webinar? I think just answer that. Yeah, we will have a recording of this webinar on the website within a week or so. So Drew, one question is about SEM and AFM. Mm-hmm. Can you comment on which one would be more, when would you use one or the other?
That's actually a great question. I would say that oftentimes SEM and AFM can be relatively complementary. When you're looking at kind of the base level analysis of what you're looking to do, and SEM is really going to dictate, it's probably the first system I would go to, and in many cases, because you could get some really rich information quickly about maybe the locations that I want to measure, or the shape or the size of features kind of in an XY domain. I would use SEM if I really want to do chemical analysis of anything that's on the surface as well. AFM really kind of stands in as a complement to SEM for looking at things when we want to maybe measure discrete feature sizes that we can't see in Z on the SEM. Or AFM is where if we can't see the features that we want to see with an SEM, AFM is the easiest way to really get after that. Because we can go to basically, we can image things that are an order of magnitude, maybe even more higher resolution than we can see with an SEM. I'd also go to AFM kind of as my default if I had any samples that I couldn't risk putting in vacuum or damaging with the electron beam, especially if you're a novice SEM user. It's really easy to cause problems with the SEM by burning a sample. And with an AFM, you can, generally speaking, load it, measure it, and then take that sample somewhere else without any risk of significant damage.
Okay, good. So next question is, so you mentioned mechanical measurements of soft materials, but what about hard materials? What's the limitation when you can look at hard materials?
So the kind of the cool thing about AFM is, and we didn't really dive into this too deep here, is that that cantilever that we use to actually detect the surface, we can choose the cantilever stiffness as one of the discriminating properties for setting up our measurement. So oftentimes we do a lot of work with soft materials, because AFM is really the only way to characterize mechanically things like cells. There isn't really any other system that can do those characterizations of very soft materials. When we go to harder materials, we can certainly increase the cantilever stiffness, and we can still do force curve analysis. But there are actually other systems. There are other AFM techniques that actually do a really good job of imaging the stiffness of harder materials. So we can do something like a contact resonance measurement For example, where we actually are vibrating the sample and then measuring the change in resonant frequency with a coupled probe. And that can really let us image things with an AFM that tend to be very, very stiff. Or we can use functionally a nano indenter probe. So a probe that's almost, let's say, tens of newtons of meters in stiffness to do force curve analysis. And that will work as well. I would generally say if you're looking with very, very, very thick, very, very, very hard materials and they're of a thickness that's, let's say, greater than a micron, you're probably better off using something like a nano indenter to probe those films. Why you would want to use an AFM instead of a nano indenter is if you want to have lateral resolution that's greater than that of the nano indenter. So AFM's kind of the sweet spot there, and we can take those. We can take those more better. If you have more questions, let me know. We can talk about this for hours.
Yeah, so Drew, that's a great segue actually. So one of our next webinars that we are in our planning stages is comparing a nano indenter to an AFM. So please stay tuned. We will have a, we'll post about when that webinar is going to be. So there's a bunch more questions that's popping up. So Drew, if you can keep your answer a little shorter.
Of course, yeah.
So can you talk a little bit about the magnetic module? How do you image with that?
Yeah, so one of the things, again, with this AFM cantilever, you can actually, you basically put a magnetic moment on the end of the cantilever. You can image topography, and then in what's called a lift pass, you can basically move the AFM probe above the surface, and then sense the long-range forces where you have a magnetized probe, and you can actually measure discrete features where there's magnetic moments underneath the probe. It's relatively straightforward, and we can send you information on that.
Okay. So is there any technique recommended for curved samples or non-flat samples?
It really depends on the magnitude of the curvature. What's really great about doing nanoscale analysis is if you're using like a millimeter diameter, ball at the AFM scales, 10 microns by 10 microns, things are still relatively flat. If you're looking to do, things that have a really high aspect ratio of curvature, on that nanoscale, the stylus profilometers work great for measuring large feature curves. So things like, lens arrays. If you want to measure the asphericity of a lens, a stylus profiler might be the way to go.
Okay. The next one is, I know AFM can be used in rubber applications. Is it in natural rubber research or in tire industry?
Both. Yeah, AFM's been used in both. The hardest thing to do in any of the rubber analysis is doing sample prep. Actually doing AFM on any rubber or elastomer is relatively straightforward, as long as you can prep the samples to be flat. So generally that means using something that's called a cryomicrotome. Again, we are very knowledgeable about this and be happy to take your questions and kind of guide you in the right direction. This is relatively trivial is probably the wrong word, but it's something we do all the time.
Okay. How about characterization of corrosion samples? Do you want to take this separately?
Yeah,
it's a longer answer, I guess.
Absolutely. I mean, the short answer is yes. We can actually, electrochemically, we can induce corrosion, so that's kind of cool. So you could do in situ analysis, or if you're going to measure corrosion pits. Yeah, let's do this offline because this depending on what the application is, it'll dictate where we go, and we're happy to answer this question honestly and clearly.
Okay, yeah. So the person who signed up for this, who has this question, is signed up as an anonymous attendee. So if you can please contact us directly, onto one of our emails, info@nanosurf, or any one of our contact emails, we'll get back to you on that. Can we conclude the resolution of AFM also depends on the tip radius of the cantilever?
That is a great question, and the short answer to that is yes and no. If you're operating in what's called contact mode, the tip radius is your limiting or discriminating factor. If you're operating in tapping mode or dynamic mode, as we call it, you can actually resolve structures that are much, much, much smaller than the end radius of the tip. Again, just take my word for it. We can show you the examples, but if you really want to go into the physics and have a discussion about it, I'd love to have that discussion. And I can point out why that is. But the short answer is no, the AFM resolution is not dependent on the tip radius of the cantilever. We could go to much higher resolution than that.
Okay. Another interesting question. Why is it important for a scientist to see 3D image of a sample?
Wow. That's a great question. I mean, I think it really depends. It really depends on what your research is. I mean, oftentimes, if just making it if you get enough information from just a two-dimensional picture and you don't need that third dimension, then you don't necessarily care. But it's the third dimension is a great way to characterize differences between samples. You know, if you're doing different process preparations for a thin film deposition or a surface treatment, or even if you're growing two-dimensional materials, that third dimension gives you an extra degree of freedom to characterize your samples and understand your situation much better. I mean, I think we're in the business of asking and answering questions as scientists. That's really what we do. And I think anytime that we can get more information that gives us a deeper insight into our fields, it's always a good thing. So I think philosophically, I would say, we live in a three-dimensional world, and we want to explore things as deeply as possible, and that's why the third dimension is kind of critical.
Okay, so there's another request actually here. Can we have a detailed PFM demo in the near future? I'll take that answer and say yes. We will schedule one soon. And like I said, please follow us on our LinkedIn page, or follow our website. We have a page set up now just for all these new online demos and online webinars, and we'll also send out emails. So we will set up one for PFM soon.
Yeah, and I think if the follow up to that, if you need to get a detailed PFM demo much sooner than we're going to do it for the webinar series, just give us a call and we can always set something up for you that's a little bit more personalized.
Yeah. So that's not only for PFM, but it's for any demo. If any of you are interested in any kind of demo, please contact us, and we'll try and work out something so that we can do a demo for you.
Yep.
So there was another question. The maximum sample size of an AFM is unlimited using tip scanner. Is this a lock spec for NanoSurf? I don't know. Do you want to take it?
No, absolutely no. Listen, no, it's not. There are tips. So you can design an AFM in three different ways. You can have a sample scanner, a decoupled scanner, or a tip scanner. And a decoupled scanner is simply a hybrid where the sample moves in X and Y, and the probe moves in Z. There are a number of commercial companies out there that make AFMs. Each could choose to make sometimes multiple designs within their product portfolio. We choose to make tip scanners because long and short of it, we find them to be the most ubiquitous. It gives you the greatest degree of freedom for measuring your samples. But there are some drawbacks to tip scanners. We could delve into that in a different webinar or a different conversation. But it is not a lockout spec for NanoSurf. There are other tip scanning AFMs out there. It's actually much harder to make a really good tip scanning AFM though. I will say that, and it's why you won't find many of them on the market anymore, because to make a high quality AFM that can actually do the measurements that we were showing today in a tip scanner, that is the greatest degree of difficulty in the kind of manufacturing design and engineering. And it's one of the reasons I joined NanoSurf, is because I was just really proud of the fact that NanoSurf can do this and do this really, really well.
Okay, thanks, Drew. I think we've answered most of them, but there are a couple more questions that hasn't been answered. We'll try and get back to you directly. But at this point, I think we should call this a day. And thank everybody for attending, and thank you, Drew. Thank you for a great presentation.
Yeah, thank you everybody for coming. I hope you found it useful. I certainly really appreciate the questions, and again, feel free to reach out. I probably should have put my email address on the tail here, but it's griffin@nanosurf.com. Send me a note. I'd be happy to talk to anybody anywhere in the world. And this is what we do. We're here to help serve you and help make your lives better. And we're all stuck at home these days, so we've got we do have a little bit more extra time to have more detailed conversations.